Now that we've seen the pseudocode and the algorithm, let us analyze the algorithm, ergo its time and space complexity. First of all, we know that Dijkstra's algorithm is a greedy algorithm, which essentially means that it does not take all the possibilities into account and then chooses the best one. Rather than that, it chooses a node and then only considers the adjacent nodes to it and chooses best possible or the shortest among those. In this case, it chose 2 for the next iteration. Now let's explore the time complexity of the algorithm. As we saw, it goes through all the vertices of the graph, and at every iteration it chooses the node with the minimum possible distance from the starting node among all the unvisited nodes. Now this also means that it depends on the graph, but in the worst possible case it will be a complete graph where all the nodes are connected to all the other nodes, and at every iteration for every node we'll be looking at all the adjacent nodes and trying to relax all the adjacent nodes, in which case we can take the time complexity to be v square in the worst possible case, v being the number of vertices. But as we find out that this is only the case in the naive implementation. If we represent the graph as adjacency list and use binary heap to find out the node with the shortest possible distance from the first node, we will get a time complexity which will be O of log v into E. Now, what are these modifications? As a very brief overview, this V got converted into E because we are using the adjacency list as a data structure to represent the graph. An adjacency list is basically just a list of vertices of the graph in a V cross V matrix with every cell representing the weight of that particular node, and the weight will be 0 if those particular nodes are not connected at all. And where does this log V come from? This log V comes from the data structure which I just talked about, called a binary heap, which helps you find out the node which is the least distance from the starting node among all the unvisited nodes. Basically, we can just access the binary heap and find out the shortest distance node from that in an order of log n, here n being the number of elements in the binary heap, and in this case n will be equal to v being the number of vertices. Now, talking about space complexity is pretty straightforward. In this case, we will be storing an adjacency list of the graph and a binary heap, bringing the space complexity to be roughly O of v square, because the binary heap will only add a linear element to it.